Watch a fitness app tell you your squat is too shallow, or a film studio turn an actor's movement into a digital character. Both of them rely on the same underlying capability. They can find where a person's joints are and how those joints are arranged in space. That capability is called pose estimation, and today we're breaking down how a machine looks at a flat image and reconstructs the posture of the human body inside it, one joint at a time. Now, to see what makes this different, let's compare it with plain object detection. Object detection draws a box around a person. That box tells you someone is present and roughly where they are in the frame. But it says nothing about what that body is actually doing. A person standing, sitting, reaching up, or falling over all get the exact same rectangle. The posture inside, it is completely invisible to the system, and so is any sense of movement. Pose estimation goes inside the box. Instead of one rectangle, it locates the individual body joints, the shoulders, elbows, wrists, hips, knees, and ankles, plus a few points on the head, and then connects them into a skeleton. Now the machine doesn't just know a person is there. It knows the shape and the movement of that person, frame by frame, which is exactly what a form checker or a motion capture rig needs. So how does a model actually go from raw pixels to a skeleton? Follow the 4 steps of the pipeline. First, the model scans the image and finds candidate body joints. It's looking for the visual signature of a shoulder, a wrist, an ankle, wherever those patterns happen to appear across the whole picture, without yet worrying about how they fit together. Then it localizes each joint precisely. Modern methods usually predict a heat map for every joint type, a probability map that glows brightest exactly where that joint most likely sits, and the peak of that map becomes the joint's pixel location. A heat map handles uncertainty far better than guessing a single coordinate outright. After that, it connects the dots. The scattered joints get linked into a skeleton following the anatomy of the body. So an elbow attaches to the right shoulder and the right wrist, not to some random point on the far side of the frame. And when several people share the frame, there's one more job. The model has to group joints to the correct person, sorting out whose elbow belongs to whose shoulder, so that 2 people standing close together don't get tangled into one impossible body with 3 arms. Now, let's pull out the ideas that carry this whole task, because they're worth holding on to. Locate the key points. At its heart, pose estimation is finding a set of key body joints and treating each one as a labeled point in the image. Everything else builds on getting those points right in the first place. Build the skeleton. Isolated points aren't enough on their own. The real output is the arrangement. The joints wired together into a connected figure that captures posture and motion and can be tracked smoothly over time across a video. Handle the crowd. For multiple people, there are 2 dominant strategies. The top-down approach first detects each person, then finds joints inside each box, which is accurate but slows down as the crowd grows. The bottom-up approach detects all the joints at once, then groups them using learned associations, which stays fast even when the scene is packed. All right, let's lock into 4 things to remember. Pose estimation locates the key body joints of a person as key points, and it goes far beyond a simple bounding box. Those joints get connected into a skeleton, which captures the body's posture and movement across each frame of a video. For scenes with many people, top-down methods detect each person first, while bottom-up methods find every joint and then group them, staying fast in a crowd. From motion capture in film and games to fitness form checks, sports analytics, sign language, and augmented reality, this one skill shows up nearly everywhere. If you enjoy having AI ideas explained in plain language, come spend a little time over at Standarity.com.